Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will review surds. So remember, a surd is just an irrational number whose exact form involves a radical. What do I mean by that? Well, something like root 4 is not a surd because square root of 4 is 2. 2 is rational. But on the other hand, the square root of 3 is a surd. It's irrational. Its decimal expansion is about 1.732. It goes forever and there is no pattern. So this is a surd. Root 3 is said to be in exact form. So notice here we have the radical, which is just a root sign. So let's first look at simplifying surds. We just find the largest possible square factor and use this simple rule here. So if I want to simplify, say, square root of 117, it's kind of like simplifying fractions. I want to find a number that has the same value but is written with smaller numbers. In this case, we want a smaller number inside the radical. So what we have to do is go through square numbers and find which is the highest of these that goes into 117. Turns out it's 9. So I can write root 117 as root 9 times root 13. The reason we chose 9 of all numbers is it's a factor of 117 and it is also a perfect square. The reason this simplifies because root 9 is equal to 3. I can just write this as 3 root 13. These two numbers are equal in value. This is said to be simpler because there is a lower number under the square root. Now, if you have something like this and you want to go the other way, basically unsimplify it, to move a number under the square root, you need to square it. So this is the same as square root of 2 squared times 3, which is equal to square root of 4 times square root of 3 is just the square root of 12. So if I wanted to simplify square root of 12, it would look like this. Note that a similar process works if you want to simplify, say, cube roots or fourth roots. So if I wanted to, say, simplify the cube root of 81, I find the highest perfect cube that goes into 81. That's 27. 27 is 3 cubed, so I would write this as cube root of 27 times cube root of 3. The cube root of 27 is 3. This here is said to be simpler because we have a lower number under the square root. All right, let's now look at adding and subtracting surds. So we can only add or subtract like surds, but sometimes you'll need to simplify first. So let's explain what I mean. Let's say I want to simplify this here. Well, I have to take the root 5s together and the root 3s together. It's kind of like terms in algebra. These are like x's, these are like y's. So 2 root 5 plus 2 root 5. It's like 2x plus 2x is 4x. 2 of something plus 2 of something, you now have 4 of something. I have to do the root 5s and the root 3s separately because they're like surds. So negative root 3 minus 4 root 3, we're just going to add the coefficients. Nothing in front means 1. Negative 1 minus 4 is negative 5. So this will just be negative 5 root 3. I can't simplify this any further. These are not like surds. Now, what this second point means is sometimes you get an expression like this. It probably looks like you can't simplify this at all because root 90 and root 40 are not like surds. But what we're going to do is first simplify them. So I'm going to leave the 2 alone. Now, the highest square number that goes into 90 is 9, so I can write root 90 as root 9 times root 10. Similarly, for root 40, I choose 4 and 10 because 4 is the highest perfect square that goes into 40. I couldn't choose 20 and 2 because they're not perfect squares. So let's simplify this one. 2 times 3, root 9 is 3, times root 10 is 6 root 10. Root 4 is just 2. So what I have here is 6 root 10 minus 2 root 10. These absolutely are like surds. This will just give me 4 root 10. So always first check if you can simplify before trying to add or subtract surds. All right, let's look now at rationalizing the denominator. So if we look at something like 4 over root 7, its denominator is irrational. So when we rationalize the denominator, we don't want to change the value of this number. We want to find a number that has the same value but has a rational denominator. So what we're going to do is times top and bottom by something to make this rational. What could I possibly times by root 7 to make it rational? Well, I could just multiply by itself. Root 7 times root 7 is 7. That is rational. That's the definition of a square root. So if I times the bottom by root 7, I must times the top by root 7, else I would change its value. So on top, I just have 4 root 7. So these two numbers here and here have the same value, but this one has a rational denominator. What about here? Here I want to write this with a rational denominator, but I can't just times top and bottom by root 7. If I times the bottom by root 7, I get 7 plus root 21. It's not rational. When you have an expression like this on the bottom times by its conjugate. So what do I mean by conjugate? I mean the same thing with the same terms, same two numbers, root 7 and root 3, but a different sign in between. So why does that actually help? Well, it allows us to use the difference of two squares. See, when you have these two being multiplied together, you simply square the first, square the second, and stick a minus between them. So squaring root 7, I get 7. Squaring root 3, I get 3. If I put a minus between them, 7 minus 3 is just 4. Now I have a rational denominator. But once again, if I multiply the bottom by a number, root 7 minus root 3, so too I must multiply the top by that number, otherwise I'd be changing its value. So when you're doing these multiplications, you might want to put brackets around to help you. I need to times 4 by root 7 and root 3. So I simply get 4 times root 7, 4 times root 3. So I can factorize the top, take out a common factor of 4, and then I can divide top and bottom by 4. The simplest way to write this is root 7 minus root 3. Now this is said to have a rational denominator because I can write it over 1. All right, let's now look at a harder problem. So let's simplify this expression here. So when you have multiple terms, multiple things on top and the bottom, always be on the lookout to see if you can factorize. See if there's a common factor. Now, it's probably not obvious what the common factor is here. So let's see if we can simplify each individual surd. So root 45, highest square factor is 9. And similarly, for root 18, the highest square factor is 9. All right, so on the bottom, I can't really simplify either of these. Just like fractions, not all surds can be simplified. But I can write root 15 as root 5 times root 3, and I can write root 6 as root 3 times root 2. So on the top, I have 3 root 5 plus 3 root 2, and on the bottom, I have a common factor of root 3. So I'm going to take out root 3. It's being multiplied by root 5 to get the first term and root 2 in the second term. Of course, I can factorize this top as well. I can write that by taking out a common factor of 3 as 3 bracket root 5 plus root 2. So now I have something on the top and the bottom. I can cross it out. As long as it's a factor. You can cross out anything as long as it's being multiplied on the top and the bottom. So crossing that out, I'm left with 3 over root 3. In order to write that with a rational denominator, I times top and bottom by root 3. Top becomes 3 root 3. The bottom simply becomes 3. Crossing those out, my final answer is simply root 3. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.